So next on our list of possible terms is our simple pole. So we see this is very similar to our simple zero, it's just that now this term is in the denominator of our transfer function. So again, our ultimate goal here is to get our gain and our phase in terms of, or plotted against our frequency. But first, let's take a closer look at getting the magnitude and phase of this transfer function. So we have 1 divided by 1 plus j times omega over p1. Okay, so we have our denominator in rectangular form right now. If we get it into polar form, it's going to be easier to do this division here. So we can write this numerator as 1 angle 0 to convert it into polar form. Our denominator, of course, isn't going to be so straightforward, so we're going to have the square root of 1 squared plus the square root of omega divided by p1 squared. And the phase angle is going to be inverse tangent of omega over p1 divided by 1. Okay, so now to do this division, we're going to divide our magnitudes. So our magnitude is going to be 1 divided by the square root of 1 squared plus omega divided by p1 squared. And to get our overall phase angle, I'm going to subtract the denominator phase angle from the numerator phase angle. So I get 0 degrees minus the inverse tangent of omega over p1. Okay, so now we have our magnitude and phase. So let's take a closer look at each one of those. So if we want to plot our gain in decibels, we're going to say our G, so dB, is equal to 20 log of the magnitude of our function. So our magnitude is here. And so instead of writing it like this, what I can do is I can say this is actually just square root of 1 squared plus omega over p1 quantity squared to the power of -1. So let me clean up my brackets here. So let's put all of this in here. And let's put that -1 on the outside of the parentheses inside the brackets. Okay, so it's just 1 over that. And so again, with our log properties, we can bring that exponent, that -1, out front and multiply it by the 20 so that we get the gain in decibels is equal to -20 times log. And now we just have the square root of 1 squared plus omega over p1 squared. So we recognize now that this looks exactly the same as, well, so not exactly the same. It looks the same as what we saw for our simple zero. The only difference is this negative sign out front. And so what that means, so let's just write that. This is almost the same as our simple zero. The only difference is now we have a slope of -20 dB per decade. And of course now our corner frequency is going to be related to that pole instead of the 0. So our corner frequency, our break frequency, our 3 dB frequency, however you want to call it, this omega is now equal to our P1. So let's come up here and plot what that looks like. So we have sort of, if we want to look at the most limited case, let's say we have our P1 here. This is 1/10 of P1, and this is 10 times P1, so we have a log scale for our frequency. And so what we're saying is that we have a -20 dB per decade slope, so let me go ahead and put a -20, and we're saying that the same way that we did with our simple zero, we're saying that our sort of break frequency is here at P1. So anything less than that, we're going to have a a gain in decibels of 0. And once we exceed that corner frequency, we're then decreasing with the slope of 20 dB per decade. And of course, that just continues going there. So this is a slope of negative 20 dB per decade. So we get something that looks like that. So now let's consider our phase. Okay, so for our phase information, now we're looking at this component here. So we have 0 minus the tangent, so really that just becomes negative inverse tangent. So our phase is equal to negative inverse tangent of omega 1 over P1. And so again, this becomes very similar to our simple zero. So similar to our simple zero. The only exceptions is that, of course, now our key frequency is this P1, and we have a slope of negative 45 degrees per decade. So negative 45 degrees per decade, and our sort of key frequency, which we said was where our phase angle is, in this case, negative 45 degrees, is going to be the P1 as opposed to Z1 before. So if we come up here, let's again add our frequencies. So let's say we have a tenth of P1, P1, and 10 times P1. So we get something that looks like that. And our key phases in this case are going to be our negative 45 degrees and our negative 90 degrees. So we're saying at a value of P1, we have negative 45 degrees. And again, we didn't show all that in as much detail, but it's the same idea as what we saw for our simple zero. So at P1, we have a phase angle of negative 45. At 10 times P1, we're approximating it as negative 90. And at a tenth of P1, it's approximately 0. So below that tenth of P1, it's staying at 0. And above 10 times P1, it's staying at negative 90. And so that continues on. And in between, we're doing sort of this linear approximation with a slope of negative 45 degrees per decade. So we get something that looks like that. And so that covers our simple pole.